Picture standing under a night sky so clear, so vast, that it feels like the universe is breathing right above you. Every twinkling star, every faint smear of distant galaxies, they aren't just points of light. They're pieces of a puzzle humanity has spent centuries trying to solve. And here's the wild part. Just when we think we've got it figured out, space throws us another curveball. A discovery so mind-bending it rewrites the textbooks. That's the thrill of cosmic exploration. We're always on the edge of learning something that shatters what we thought we knew. Take black holes, for example. A century ago, they were just a quirky idea in Einstein's equations. Today, we've not only proven they exist, we've snapped a picture of one, a monstrous void swirling with the ghosts of swallowed stars. Or consider dark energy, this mysterious force pushing the universe apart faster and faster. It's like the cosmos is playing a game we don't even know the rules to yet. These aren't just scientific footnotes, they're seismic shifts in how we see our place in the grand scheme of things. That's what this journey is about. The 25 space discoveries that didn't just add to our knowledge but flipped it upside down. From the echoes of the Big Bang to rogue planets drifting between stars, each one is a reminder. The universe is stranger, more violent, and more beautiful than we ever dared imagine. So buckle up. By the time we're done, you'll see the night sky differently, not as a static backdrop, but as a living, evolving story we're only beginning to decode. And trust me, some of these revelations, they'll haunt you in the best possible way. Let's rewind to 1964, when two radio astronomers named Arno Penzias and Robert Wilson were tinkering with a giant horn-shaped antenna in New Jersey. They kept picking up this faint, persistent static no matter where they pointed the antenna. It was there. At first, they blamed pigeons nesting in the dish. But after scrubbing away bird droppings and chasing off the feathered culprits, the noise still didn't go away. That annoying static, it turned out to be the oldest light in the universe, the afterglow of the Big Bang itself, stretched over 13 billion years into a whisper of microwaves. This cosmic microwave background radiation was the smoking gun scientists had been hunting for. It proved the universe hadn't always existed in some serene, unchanging state. Instead, it began in a violent explosion of energy, a bang so colossal it set space itself expanding outward like a balloon inflating. Suddenly, the vague idea of a beginning had hard evidence. And here's what's wild, that faint static isn't just ancient light, it's a map. Tiny variations in its temperature, imperceptible flickers, reveal the seeds of everything we see today. Those microscopic fluctuations, they're the blueprints for galaxies, stars, even us. Without them, the universe would have been a featureless soup of particles. But the real kicker, the Big Bang theory didn't just explain where we came from, it reshaped how we think about time. Before this, even Einstein imagined the cosmos as static and eternal. Now we know it has a birthday, a lifespan, maybe even an expiration date, and that microwave hum, it's still ringing in our ears, cooling as the universe stretches, a fading echo of the moment everything began. So next time you hear static on an old radio, remember, you're eavesdropping on the universe's first breath. Now let's talk about something you'll never see, but without it, the universe as we know it would fall apart. In the 1970s, astronomer Vera Rubin was studying galaxies, those swirling islands of stars, when she noticed something bizarre. The outer edges of galaxies were spinning way too fast. According to the laws of physics, those distant stars should have been flung into the cosmic void, like water droplets spinning off a wet bicycle wheel. But they weren't. Something invisible was holding them together with an irresistible gravitational grip. Vera had stumbled upon the fingerprints of dark matter, an enigmatic substance that doesn't emit, absorb, or reflect light. It's completely transparent, yet it outweighs all the stars, planets, and cosmic dust we can see by a factor of 5 to 1. Think about that. everything visible in the night sky, every galaxy, every nebula, is just the glitter on top of a mountain we can't see. Here's where it gets even stranger. We still don't know what dark matter is. It could be exotic particles left over from the Big Bang, or something even weirder that defies our current physics. What we do know is that without it, galaxies wouldn't exist. Dark matter's gravitational scaffolding pulled ordinary matter together in the early universe, creating the cosmic web where stars and planets eventually formed. And the mystery deepens. Recent observations suggest dark matter might be clumpier than we thought, or that its behavior changes over time. Some theories even propose it interacts with itself in ways we can't yet detect. Every new telescope, every particle detector buried deep underground, brings us closer to cracking this puzzle. But for now, dark matter remains the universe's silent architect, shaping everything from the largest galaxy clusters to the fate of the cosmos itself. One thing's certain: when we finally unravel its secrets, it'll rewrite physics as profoundly as Einstein's relativity did. Until then, we're left staring at the stars, knowing most of what's out there is hiding in plain sight. Just when we thought we had the universe figured out, it threw us another curveball, one so baffling it made dark matter seem almost ordinary. In 1998, two teams of astronomers were studying distant supernova, the explosive deaths of massive stars, expecting to measure how much the universe's expansion was slowing down. After all, gravity should have been pulling everything back together like a cosmic tug of war. But the data told a different story. The universe wasn't just expanding, it was accelerating, as if some invisible hand had pressed down on the gas pedal of spacetime itself. The culprit: dark energy, a mysterious force that makes up about 68% of the universe and behaves like the opposite of gravity. Instead of pulling things together, it pushes them apart, harder and faster as space stretches. Imagine blowing up a balloon with tiny dots on its surface. Now imagine the dots aren't just moving apart as the balloon inflates, they're speeding up. That's dark energy in action. What makes this discovery so unsettling is what it implies about the fate of everything. If dark energy keeps strengthening, the universe could end in a big rip, where galaxies, stars, even atoms are torn apart by runaway expansion. Or it might dilute matter so thoroughly that the cosmos becomes a cold, empty void trillions of years from now. But here's the twist: we don't even know if dark energy is constant. What if it fluctuates? Could it one day reverse and crunch the universe back into a singularity? The wildest part: we're clueless about what dark energy actually is. Some think it's a property of space itself, Einstein's cosmological constant, making a comeback. Others propose it's an unknown energy field permeating the vacuum of space. There's even a chance our understanding of gravity is fundamentally flawed. Every telescope, from Hubble to the upcoming Nancy Grace Roman Space Telescope, is hunting for answers. One thing's certain: dark energy rewrote the cosmic playbook. It's a reminder that the universe isn't just expanding, it's evolving in ways we're only beginning to grasp. And until we crack this enigma, the ultimate fate of reality remains one of physics' greatest unsolved mysteries. For centuries, astronomers assumed our solar system was the blueprint for how planets formed, a neat arrangement of worlds orbiting a single star at predictable distances. Then in 1995, everything changed. Two Swiss astronomers, Michel Mayor and Didier Queloz, pointed their telescope at 51 Pegasi, a star much like our Sun 100 light-years away, and detected something impossible. A gas giant half the size of Jupiter whipping around its star in just 4 days closer than Mercury orbits our Sun. This was 51 Pegasi b, the first confirmed exoplanet ever found around a Sun-like star. And it defied every expectation. According to existing theories, gas giants couldn't form so close to their stars the heat and radiation should have prevented it. Yet there it was, a hot Jupiter blazing a trail into uncharted cosmic territory. overnight, our understanding of planetary systems shattered. If planets could exist in such extreme orbits, what else was out there? The answer came fast. Within years, new detection methods like measuring the slight dimming of starlight as planets passed in front of their suns revealed thousands more worlds. Super-Earths, ocean planets, even diamond-rich worlds orbiting pulsars. The diversity was staggering. Some systems had planets packed tighter than peas in a pod, while others featured lone giants drifting through the void. But the real revolution wasn't just the sheer number of exoplanets, it was what they told us about our place in the cosmos. We now know planets outnumber stars in the Milky Way, with billions potentially habitable. Earth went from being a presumed rarity to just one of countless possibilities. And with telescopes like James Webb analyzing exoplanet atmospheres for signs of water or even life, we're closer than ever to answering humanity's oldest question: are we alone? 51 Pegasi b was more than a discovery, it was a cosmic wake-up call. The universe, it turns out, is far more creative with its planetary designs than we ever imagined. And somewhere out there, around one of those distant suns, another world might just be looking back at us, wondering the same thing. Einstein's theory of relativity had a wild prediction. When massive objects like black holes collide, they should send ripples through the fabric of space-time itself, gravitational waves. For decades, scientists chased this phantom. Then, on September 14, 2015, at 5:51 in the morning, a machine called LIGO, the Laser Interferometer Gravitational Wave Observatory, picked up something extraordinary. A signal so faint it moved the detectors by less than 1,000th the width of a proton, yet so powerful it carried the echo of two black holes, each 30 times the mass of our Sun, spiraling into each other 1.3 billion years ago. This wasn't just a discovery, it was a revolution in how we experience the cosmos. Until then, astronomy had been all about light. Telescopes captured photons from stars, galaxies, and nebulae, painting the universe as a silent movie. But gravitational waves, they let us listen to the universe for the first time. That chirp LIGO detected converted into sound was the literal shockwave of space-time ringing like a bell. Imagine being deaf your whole life and suddenly hearing the crash of ocean waves. That's how profound this moment was. What's even crazier is how these waves betray secrets light can't. When black holes merge, no light escapes. It's the ultimate cosmic stealth event. But gravitational waves barrel straight through, carrying details about the black hole's masses, spins, and even the warped geometry of space-time around them. Since that first detection, LIGO and its European counterpart, Virgo, have caught dozens more mergers, including neutron stars colliding in a fireworks show of gold and heavy elements. Here's the kicker, this is just the beginning. Future detectors like the space-based LISA mission will tune into lower frequencies, hearing supermassive black holes merging at the hearts of galaxies. Somewhere in those vibrations, we might finally catch whispers of the Big Bang itself. Gravitational waves haven't just confirmed Einstein, they've handed us an entirely new sense, turning the universe into a symphony we're only starting to decode. And like any great piece of music, the more we listen, the more we realize how much we've been missing. For over 100 years, black holes existed only as mathematical monsters, Einstein's equations predicting regions of space where gravity is so intense, not even light can escape. We knew they had to be real. We'd heard their mergers through gravitational waves, seen stars torn apart by their tidal forces, but actually seeing one. That seemed impossible. Then, in April 2019, the Event Horizon Telescope collaboration unveiled an image that stopped the world in its tracks. A fiery ring of light encircling a perfect, abyssal darkness at the heart of galaxy Messier 87, 55 million light-years away. This wasn't just a picture, it was a triumph of human ingenuity. The Event Horizon Telescope wasn't a single instrument, It was a network of 8 radio observatories spanning the globe, from Hawaiian volcanoes to Antarctic ice, synchronized to act as one Earth-sized lens. The data collected in one night was so vast it couldn't be sent digitally. Hard drives had to be physically flown to supercomputers. 2 years of processing later, we had our first glimpse of a black hole's shadow, the silhouette of its event horizon backlit by superheated gas swirling at near light speed. What makes this image so revolutionary? First, it confirmed general relativity's predictions with stunning precision. The ring's size and shape matched Einstein's math even in this extreme environment. Second, it revealed how black holes feed. That lopsided brightness in the ring, that's the Doppler effect from gas rotating toward us at mind-bending velocities, showing these cosmic behemoths aren't just vacuum cleaners, they're chaotic, dynamic engines. But perhaps the most profound impact was cultural. Suddenly, an abstract concept became visceral. People who'd never pondered space-time curvature shared the image on social media, mesmerized by its eerie beauty. It bridged the gap between scientific theory and collective imagination, proving that even the universe's most enigmatic objects could be brought within reach. Now the real work begins. With new telescopes joining the array, we'll soon capture sharper images, maybe even a movie of a black hole's turbulent surroundings. And somewhere in that darkness lies the next great mystery: what happens to information swallowed by the singularity? Does it vanish forever, or is there some quantum trickery we've yet to uncover? One thing's certain, that smudgy orange ring isn't the end. It's the threshold. In 1995, astronomers made a bold gamble. They pointed the Hubble Space Telescope at a patch of sky near the Big Dipper, a region so seemingly empty, one scientist called it the most boring part of the universe. For 10 straight days, Hubble stared at this cosmic void, collecting photons so faint they'd been traveling for over 12 billion years. When the image finally processed, it wasn't emptiness that filled the frame. It was fire. Thousands of galaxies, spirals, ellipticals, irregular blobs packed into an area the size of a grain of sand held at arm's length. The Hubble Deep Field didn't just capture distant objects. It ripped open a window to the ancient universe, revealing a truth more staggering than anyone had dared to imagine. What makes this image so revolutionary isn't just the sheer number of galaxies. It's what they represent. Each smudge of light is an island of billions of stars, many from when the universe was less than half its current age. Some are so young, they're still forming stellar nurseries glowing with newborn suns. Others show signs of cataclysmic collisions, galaxies tearing each other apart in slow motion. The diversity is dizzying, and here's the kicker: this wasn't some special cluster or crowded region. This was a random slice of the cosmos, proving that no matter where you look, the universe is dense with galaxies. The implications shattered our cosmic perspective overnight. If this tiny patch held thousands, then the observable universe must contain hundreds of billions of galaxies. Suddenly, the Milky Way wasn't just one of many, it was a single speck in an ocean of stellar cities. But the real magic lies in what the deep field didn't show. Those black gaps between galaxies, they're not empty. Modern telescopes like James Webb have since peered even deeper, finding galaxies so far away their light was stretched into infrared by the universe's expansion. Some may be from the cosmic dark ages, just a few 100 million years after the Big Bang. Yet the deep field's legacy isn't just about scale, it's about humility. That boring patch of sky forced us to confront how little we truly see. Every star you can spot with the naked eye, they're all in our own galaxy. The deep field revealed the universe's hidden layers, like lifting a microscope to a drop of pond water and discovering an entire ecosystem. And it sparked a new era of exploration: ultra-deep fields, multi-wavelength surveys, even citizen science projects classifying galaxies by their shapes. What began as a risky observation became a cosmic census, proving the universe is both richer and stranger than we'd dreamed. And somewhere in that sea of galaxies, there's another message. If the cosmos is this crowded, how many other eyes might be looking back, wondering the same thing? Mars has always been the cosmic neighbor that teased us with possibility. A rust-colored world with polar ice caps, seasons, even a day just 40 minutes longer than ours. But for decades, one question haunted scientists. Where did its water go? The answer, it turns out, was hiding in plain sight, not just in Mars' distant past, but pooled beneath its surface right now. The first clues came from NASA Viking orbiters in the 1970s. Their images revealed what looked like dried-up river valleys, floodplains, even ancient shorelines. But without boots on the ground, we couldn't be sure. Then, in 2004, the Opportunity rover stumbled across something definitive: tiny spherical concretions nicknamed blueberries, made of hematite, a mineral that forms in water. That same year, Europe's Mars Express orbiter detected something even more tantalizing: faint radar reflections hinting at liquid water beneath the southern ice cap. The game-changer arrived in 2015. NASA Mars Reconnaissance Orbiter spotted streaks on steep slopes that appeared and vanished with the seasons. They called them recurring slope lineae, and their best explanation: liquid water salty enough to stay liquid in Mars' freezing temperatures, seeping to the surface. But the real bombshell came 3 years later. Using ground-penetrating radar, scientists found a 20-kilometer-wide lake of liquid water buried under a kilometer of ice at Mars' South Pole. Not just damp soil, an actual subsurface lake, possibly kept liquid by dissolved salts or geothermal heat. What does this mean for life? On Earth, where there's water, there's almost always life, even in the most extreme environments. Mars' ancient river valleys suggest it was once a wet world, maybe even an ocean world for billions of years, long enough for life to emerge. The Perseverance rover is hunting for answers right now in Jezero crater, an ancient lakebed filled with clay minerals perfect for preserving fossilized microbes. But here's the twist: if that buried lake really exists, it could be a refuge for life today. Microbial extremophiles cut off from the surface for eons might still be clinging on in those dark, briny waters. Future missions like Europe's Rosalind Franklin rover could drill for samples, and if we find even dormant bacteria, it would mean life isn't a fluke of Earth, it's a cosmic inevitability. The story of Mars' water isn't just about a barren planet that once was wet. It's about a world that might still be hiding secrets in its depths, whispering to us across the void. If life could start here, just one planet over, how many other oases are waiting to be found? For most of human history, we imagine the solar system ending with Pluto, a lonely outpost drifting in the darkness. But in 1950, Dutch astronomer Jan Oort noticed something strange about long-period comets. These icy wanderers, like Halley's Comet, would swing by the Sun from all directions, not just the flat plane where planets orbit. Their paths suggested they weren't coming from nearby. They were being flung inward from a vast, spherical shell of icy debris at the very edge of the Sun's gravitational grasp. This hypothetical reservoir became known as the Oort cloud, and it's as mind-bending as it sounds. Picture a bubble of frozen relics stretching nearly halfway to the next star, an inconceivably distant region where trillions of icy bodies lurk in perpetual twilight. Some are as small as pebbles, others as massive as mountains. Most will never visit the inner solar system, but every so often, a passing star's gravity nudges one loose, sending it plummeting toward the Sun on a journey that can take millions of years. What makes the Oort cloud revolutionary isn't just its scale. It's a time capsule. These icy fragments are pristine leftovers from the solar system's birth, untouched by the heat and collisions that shape the planets. Studying comets that originate here, like the dazzling Hale-Bopp in 1997, gives us snapshots of the raw materials that formed Earth's oceans and maybe even the organic molecules that sparked life. But here's the kicker: we've never actually seen the Oort cloud. It's too far, too dark, and too diffuse for current telescopes. Its existence is inferred from comet trajectories, like deducing a hidden mountain range by tracking the pebbles that tumble downstream. Future missions like interstellar probes or advanced observatories might finally glimpse this frozen frontier. Until then, it remains the ultimate cosmic ghost, a reminder that our solar system's boundaries are far wilder and more mysterious than we ever dreamed. In the quiet pre-dawn hours of November 1967, a young graduate student named Jocelyn Bell Burnell was poring over reams of paper rolling out from a radio telescope in Cambridge. The instrument was crude, a tangled web of wires strung across 4 acres, but it was picking up something extraordinary. Every 1.337 seconds, like clockwork, a sharp pulse of radio waves blipped across the chart. At first, Jocelyn and her advisor Anthony Hewish dismissed it as man-made interference, maybe a faulty piece of equipment or even signals from a passing car. But when the pulses kept coming, always from the same patch of sky, they realized they'd stumbled onto something far stranger. The press would later dub it LGM-1, short for Little Green Men, because the signals were so precise they seemed almost artificial. What Jocelyn had discovered was the first pulsar, a rapidly spinning neutron star, the dense corpse of a massive star that had gone supernova. Imagine taking our sun and crushing it down to the size of Manhattan. That's a neutron star, and when these cosmic cinders rotate, they become cosmic lighthouses. Their intense magnetic fields funnel radiation into beams that sweep across space like the spinning light of a police car. If Earth happens to lie in the path of that beam, we see a pulse of energy with every rotation, sometimes hundreds per second. But pulsars aren't just celestial oddities. They're precision instruments that have reshaped our understanding of physics. In 1974, astronomers Joseph Taylor and Russell Hulse found a binary pulsar, 2 neutron stars orbiting each other. Over years of observation, they noticed the stars' orbits were decaying exactly as Einstein's general relativity predicted, losing energy in the form of gravitational waves. It was the first indirect proof that these space-time ripples existed, earning them a Nobel Prize and setting the stage for LIGO direct detection decades later. Today, pulsars serve as the universe's most accurate clocks. Their pulses are so regular they rival atomic timekeeping on Earth. Some, like millisecond pulsars, spin faster than a blender blade, their surfaces whipping around at nearly a quarter the speed of light. Astronomers are now using networks of these ultra-stable pulsars to detect low-frequency gravitational waves from supermassive black holes merging across the cosmos, a project called the Pulsar Timing Array. It's like turning the Milky Way into a galaxy-sized microphone, listening for the hum of colliding giants. The irony: Jocelyn Bell Burnell was famously excluded from the Nobel Prize awarded for her discovery, an oversight now widely criticized. Yet her legacy lives on every time a pulsar's steady beat helps us probe the extremes of gravity, matter, and time. These spinning stellar corpses are more than cosmic curiosities. They're the universe's metronomes, keeping rhythm with secrets we're only beginning to hear. The Big Bang gave us the universe, but something about the story didn't add up. Why is the cosmos so uniform? How could regions billions of light years apart, never having had time to exchange heat or information, share the same temperature down to a fraction of a degree? In 1980, a young physicist named Alan Guth scribbled a note to himself, a spectacular realization. He'd stumbled onto an idea so radical it would rewrite the first chapter of cosmic history: inflation. Here's the gist. Moments after the Big Bang, somewhere around 10 to the minus 36 seconds, the universe didn't just expand. It exploded, inflating from smaller than an atom to the size of a grapefruit in a fraction of a nanosecond. This wasn't ordinary expansion. Space itself stretched faster than light could keep up, smoothing out wrinkles like a cosmic iron pressing flat the fabric of space-time. And then, just as suddenly, it stopped. The energy driving this runaway growth decayed into the particles and radiation we see today, setting the stage for the slower, steadier expansion we observe now. The evidence, it's written in the cosmic microwave background, that ancient afterglow from the Big Bang. Inflation predicts ultra-precise patterns in its temperature fluctuations, like echoes of quantum jitters magnified to cosmic scales. When satellites like COBE and Planck mapped these faint ripples, they found exactly what inflation theorists expected, a near-perfect match to the mathematical fingerprints of rapid expansion. But here's where things get messy. Inflation solves big puzzles like why the universe looks the same in all directions, but it also opens wild new questions. What triggered it? Most models point to a hypothetical energy field called the inflaton, but we've never detected it. Worse yet, inflation seems to predict too many possible outcomes. Some versions of the theory suggest our observable universe is just one bubble in an endless multiverse, with other regions inflating forever under different physical laws. The biggest headache, inflation is so flexible it's hard to disprove. Critics argue it's more like a framework than a concrete theory, able to adapt to almost any observation. Yet despite the unknowns, the idea has transformed cosmology. Without inflation, we can't explain the large-scale structure of galaxies or the seeds of matter that clumped into stars and planets. It's the best tool we have to bridge the gap between the quantum chaos of the Big Bang and the orderly universe we see today. Future experiments, like measuring primordial gravitational waves imprinted on the cosmic microwave background, might finally test inflation's wildest claims. Until then, it remains the leading explanation for how our universe grew from nothingness to everything in less time than it takes light to cross a single proton. And that's the real magic of inflation. It turns the first unimaginable moments of existence into a puzzle we can actually tackle, one quantum fluctuation at a time. The universe isn't just expanding, it's moving, with entire galaxies caught in a cosmic current we can't fully explain. Back in the 1970s, astronomers mapping the large-scale flow of galaxies noticed something bizarre. Everything in our galactic neighborhood, the Milky Way, Andromeda, and thousands of other galaxies, was being dragged toward a single point in space, as if some invisible titan had its gravitational hooks in us. They called it the Great Attractor, and it remains one of the most puzzling mysteries in modern cosmology. Here's what makes it so strange. This colossal gravitational pull originates from a region roughly 250 million light-years away, near the constellation Centaurus. But there's a catch. It lies directly behind the Milky Way's galactic plane, an area so choked with dust, gas, and stars that visible light can't penetrate. Astronomers call this the zone of avoidance, and it's like trying to study a mountain peak through a blizzard. For decades, the Great Attractor was a ghost, a shadowy presence inferred only by its relentless tug on everything around it. Then came infrared and radio telescopes, which can peer through the cosmic fog. What they revealed was even more astonishing. The Great Attractor isn't just a single massive object. It's part of something far larger, the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years. At its heart lies the Norma cluster, a dense knot of galaxies with the combined mass of 1,000 Milky Ways. But here's the twist, even that isn't enough to explain the observed motion. The Great Attractor's gravity alone can't account for the velocity at which we're being pulled. There must be something behind it, something even more massive and farther away, adding to the cosmic tug-of-war. Enter the Shapley supercluster, the largest known structure in our cosmic neighborhood. Located 650 million light-years from Earth, it's a gravitational heavyweight with the pull of 10,000 Milky Ways. Some scientists now think the Great Attractor is just a waypoint, a stepping stone in a far grander flow toward Shapley's overwhelming mass. It's as if we're caught in a river with the Great Attractor as a whirlpool, but the true current leads to a waterfall we've only begun to map. What does this mean for our place in the cosmos? For one, it shatters the idea that the universe's expansion is uniform. On the largest scales, gravity is still calling the shots, with superclusters acting as anchors in the cosmic web. And the great attractor, it's a reminder that even as we peer deeper into space, some of the universe's most powerful forces remain hidden in plain sight, shaping our galactic journey in ways we're only starting to grasp. In the early 1960s, astronomers began detecting what looked like stars' pinpricks of light on photographic plates, with one glaring problem. These quasi-stellar radio sources, or quasars, were emitting staggering amounts of energy, some outshining entire galaxies by a factor of 1,000. But how could something star-sized produce such fury? The answer would rewrite our understanding of the cosmos and reveal an era when the universe was young, chaotic, and seething with violence. Quasars are the ultimate cosmic powerhouses, fueled by supermassive black holes at their cores. Picture a black hole billions of times heavier than our Sun, surrounded by a swirling disk of superheated gas and dust. As this material spirals inward, friction heats it to millions of degrees, unleashing torrents of radiation across the electromagnetic spectrum, from radio waves to X-rays. The brightest quasars blaze with the luminosity of 100 Milky Ways packed into a region no larger than our solar system. But here's the twist: these aren't local phenomena. The first quasars identified were billions of light-years away, meaning we weren't seeing them as they are today, but as they were when the universe was a fraction of its current age. What makes quasars revolutionary is what they taught us about the universe's adolescence. The most distant ones, some clocking in at just 700 million years after the Big Bang, prove that supermassive black holes grew to colossal sizes incredibly fast. That shouldn't have been possible under conventional models. How did these gravitational monsters bulk up so quickly? One theory suggests they formed from direct collapsing clouds of primordial gas, skipping the star stage entirely. Others propose they gorged on dense galactic nurseries in the early universe, where gas was plentiful and competition was fierce. Quasars also exposed the violent dynamics of young galaxies. Many are surrounded by screaming jets of plasma shooting out at near light speed, stretching hundreds of thousands of light-years into space. These jets act like cosmic blowtorches, heating surrounding gas and shutting down star formation, effectively sterilizing their host galaxies. It's a brutal feedback loop. The black hole feeds, erupts, and then starves itself by clearing its neighborhood. But perhaps their greatest legacy is how they illuminate the era of reionization. In the universe's first billion years, neutral hydrogen fogged up space, absorbing starlight. Quasars, with their blistering ultraviolet radiation, acted like cosmic blow-dryers, ionizing this fog and making the universe transparent to light. Without them, we might never have seen the galaxies that followed. Today, most quasars have gone quiet, their black holes starving as gas supplies dwindle. But their light, traveling across eons, still carries coded messages about the universe's most tempestuous chapter. They're not just relics, they're witnesses to an age when chaos ruled, and the foundations of everything we see were forged in fire. For generations, astronomers pictured galaxies as islands adrift in the black ocean of space, isolated clusters of stars separated by unimaginable voids. Then, in the late 20th century, a startling pattern emerged. When researchers began mapping the positions of thousands of galaxies in 3 dimensions, they uncovered something far grander. A cosmic spiderweb stretching across billions of light-years, with galaxies strung along shimmering filaments like dew on a spider's silk. This wasn't just random scatter, it was architecture. The universe had a skeleton, and we just glimpsed its bones. The secret to this discovery lay in 2 revolutionary tools: supercomputer simulations and deep space surveys. Theorists had long suspected that matter in the universe wasn't evenly distributed, that gravity, over billions of years, would pull material into clumps and threads. But when they ran simulations of cosmic evolution starting from the faint ripples in the Big Bang's afterglow, the results were breathtaking. The models generated intricate webs eerily similar to the neural networks of a brain, with dense galaxy clusters at the intersections and gossamer threads connecting them. Then came the Sloan Digital Sky Survey, which painstakingly mapped the positions of over 1 million galaxies. The real universe matched the simulations with uncanny precision. What makes this cosmic web so astonishing isn't just its scale, it's what it reveals about the hidden scaffolding of reality. Those glowing filaments aren't empty. They're highways of dark matter, invisible threads weaving through space, their gravity funneling ordinary gas into the strands. Where filaments cross, galaxies form like knots in a net. And the voids between them, they're not true emptiness either. Even there, you'll find the faintest clouds of hydrogen leftover wisps from the universe's birth, too diffused to collapse into stars. But here's the real kicker: this web is still growing. Gravity keeps pulling more matter into the filaments, tightening the cosmic net. In the distant future, some simulations suggest all galaxies in our local supercluster will merge into one colossal city of stars, while the voids stretch wider, isolating island universes from one another. It's a reminder that the cosmos isn't static. It's a living, evolving structure, with every galaxy from the Milky Way to the faintest dwarf caught in its grand design. And perhaps most poetic of all, we're part of it too. The Milky Way isn't just observing the web, we're embedded in one of its filaments, a single thread in the universe's tapestry. Every time you look up at the night sky, you're not just seeing stars, you're glimpsing the architecture of existence itself. Imagine a world where the sky isn't blue, but a craggy ceiling of ice stretching as far as the eye can see. Beneath it, an ocean deeper than Earth's Pacific churns in perpetual darkness, a realm untouched by sunlight for billions of years. This isn't science fiction. It's Europa, Jupiter's fourth largest moon, and what lies under its frozen crust might just be the most promising habitat for alien life in our solar system. The first hints came from NASA, a Galileo spacecraft in the 1990s. As it orbited Jupiter, its instruments detected something bizarre about Europa's magnetic field. It was fluctuating in sync with Jupiter's rotation, as if something beneath the ice was conducting electricity. The best explanation: a global saltwater ocean, its salinity making it an excellent electrical conductor. But the real smoking gun came from the moon's surface. Europa's ice shell is crisscrossed with reddish-brown cracks and ridges, features that look eerily like Earth sea ice formations. Some areas show signs of chaos terrain, where ice has broken apart and refrozen, suggesting liquid water welling up from below. Then there are the plumes. In 2013, Hubble spotted what appeared to be geysers erupting from Europa's south pole, spewing water vapor into space, a direct sample of that hidden ocean, just waiting to be analyzed. What makes this ocean so tantalizing is its chemistry. On Earth, life thrives around hydrothermal vents on the ocean floor, where mineral-rich water erupts from the planet's crust. Europa's rocky seafloor, heated by Jupiter's relentless gravitational kneading, could host similar vents. The ocean's salt content, likely containing sulfates and chlorides, mirrors Earth's primordial seas. And while sunlight can't penetrate the ice, radiation from Jupiter's magnetic field might create oxidants on the surface that could mix downward, providing energy for microbial life. That's why Europa is now one of astrobiology's holy grails. NASA's upcoming Europa Clipper mission, launching in 2024, will perform 45 close flybys using ice-penetrating radar to map the ocean's depth and chemistry. Even more ambitious, the idea of a lander that could drill through the ice, or better yet, a cryobot that could melt its way down to the water, sending back images of whatever swims in those alien depths. The implications are staggering. If life exists in Europa's ocean, it would prove that life isn't a fluke of Earth. It's a cosmic imperative, thriving wherever there's liquid water, energy, and the right ingredients. And if that's true, the galaxy could be teeming with hidden oceans, each one a potential cradle for organisms beyond our wildest imagination. Europa isn't just a moon. It's a message in a bottle floating in Jupiter's shadow, and we're finally learning how to read it. The night of August 15, 1977, was quiet at Ohio State University's Big Ear radio telescope. Then at 10:16 p.m., the machine spat out a sequence of characters that would become legendary, 6-5. It wasn't just random noise. The signal surged 30 times louder than the background static, lasted exactly 72 seconds, and then vanished, never to be heard again. The astronomer on duty, Jerry Amon, circled the printout in red pen and scribbled one word beside it. Wow, a name was born, and with it, one of the greatest cosmic mysteries of all time. What made the wow signal so electrifying wasn't just its intensity. It matched exactly the frequency scientists had predicted an extraterrestrial broadcast would use: 1420 megahertz, a quiet band where hydrogen, the universe's most common element, naturally resonates. No natural cosmic phenomenon we know of produces such a narrow, powerful burst at that frequency. And the signal's structure, it rose and fell in strength the way you'd expect if it came from a fixed point in space sweeping past Earth due to our planet's rotation, like a lighthouse beam briefly illuminating a distant shore. Decades later, we still have no definitive explanation. Was it a passing comet reflecting sunlight? Unlikely. No known comets were in that patch of sky. A military satellite, declassified records show no human-made objects transmitting at that wavelength. The most tantalizing possibility, that it was an alien beacon, remains unproven but irresistible. The signal originated near the constellation Sagittarius, a star-rich region where any advanced civilization might logically aim a message. And here's the haunting part: even if it was artificial, it would have required a transmitter millions of times more powerful than anything Earth had in 1977. The WOW signal's legacy isn't just about what we didn't find. It ignited a cultural obsession, inspiring movies, novels, and generations of scientists to keep scanning the skies. Projects like Breakthrough Listen now deploy AI to sift through petabytes of radio data, searching for patterns too subtle for human ears. Meanwhile, astronomers have revisited the original WOW coordinates with modern telescopes like the Very Large Array, hoping to catch a repeat. Silence so far, but that's the thing about cosmic mysteries, they don't expire. Perhaps the signal's greatest gift was humility. In 72 seconds, it reminded us how little we've searched. The Big Ear telescope observed that spot for less than a minute across its entire operational lifetime. Imagine tuning a radio for 60 seconds and declaring the whole planet silent. That's essentially what we've done with the cosmos. The WOW signal endures as a cosmic flare in our collective imagination, a fleeting whisper that still asks, is anyone out there? And until we know for sure, the answer will always be maybe. For centuries, the solar system seemed to end with Neptune, a tidy family portrait of planets spinning obediently around the sun. Then, in 1992, astronomers David Jewett and Jane Liu spotted something moving slowly against the starry backdrop. A tiny world just 250 kilometers wide, orbiting 3 times farther out than Neptune. This frozen speck, named Albion, was the first confirmed member of the Kuiper Belt, a sprawling graveyard of icy leftovers from the solar system's birth. And the moment we realized our cosmic neighborhood was far bigger and stranger than we'd ever imagined. The Kuiper Belt isn't just a distant curiosity, it's a time capsule. These frozen remnants never got baked by the sun's heat or squished into planets, preserving ingredients from 4.6 billion years ago like cosmic freezer burn. Some are pristine ice balls, while others, like Pluto, are complex worlds with mountains of water ice, nitrogen glaciers, and even thin atmospheres that freeze and thaw with their seasons. That's what made Pluto's demotion from planet to king of the Kuiper belt so controversial in 2006. The International Astronomical Union didn't just change Pluto's label, they rewrote the rules, declaring that planets must clear their orbit of debris. Pluto, surrounded by Kuiper belt objects, flunked the test. But here's the twist: that decision forced us to confront how alive the outer solar system really is. NASA's New Horizons mission gave us front-row seats to that chaos. In 2015, it raced past Pluto, capturing heart-stopping images of jagged ice mountains and smooth plains of frozen nitrogen. But the real surprise came 3 years later when the probe zipped by Arrokoth, a 36-kilometer-long Kuiper belt object shaped like a flattened snowman. Its two lobes, gently fused together, showed no impact scars. This wasn't a collision fragment. It was a primordial building block, preserved in deep freeze since the solar system's first million years. Arrokoth's untouched surface, stained reddish by ancient organic molecules, hinted at ingredients that might have seeded life on Earth via comet impact. Now the Kuiper belt is revealing even weirder secrets. Some objects, like Haumea, spin so fast they're stretched into ellipsoids, while others have tiny moons that might be chips knocked loose by cosmic collisions. Then there's the hypothetical Planet 9, a distant super-Earth whose gravitational pull could explain why some Kuiper belt objects orbit at bizarre angles. Whether it exists or not, the mere idea proves one thing: we've barely scratched the surface of this frozen frontier, the Kuiper belt's greatest lesson. Our solar system isn't a static museum exhibit. It's a dynamic, evolving system where dwarf planets dance, ice volcanoes erupt, and untold mysteries still lurk in the dark. And with missions like New Horizons still exploring, who knows what other frozen wonders are waiting to rewrite the story of our cosmic backyard. For billions of years, two city-sized corpses circled each other in silence. Then on August 17, 2017, their death spiral reached its climax, sending ripples through space-time so powerful they jiggled lasers in detectors here on Earth. This wasn't just another gravitational wave detection. For the first time in history, astronomers witnessed a neutron-star collision, both through vibrations in space-time and flashes of light across the cosmos, a breakthrough that solved one of the universe's greatest mysteries, where the heaviest elements in our world come from. The drama began when LIGO and Virgo gravitational wave observatories caught the signature chirp of two neutron stars merging, a crescendo rising to nearly 2,000 times per second as the stars, each more massive than our Sun but just 20 kilometers wide, whipped around each other before colliding. Mere seconds later, NASA's Fermi satellite spotted a gamma-ray burst from the same patch of sky. Within hours, telescopes worldwide swiveled toward galaxy NGC 4993, 40 million light-years away, capturing something unprecedented, a kilonova, an explosion 1,000 times brighter than a typical nova. Its rapidly fading light glowed blue at first, then reddened over days, a telltale sign of radioactive decay in freshly forged heavy elements. Here's why this was revolutionary. For decades, scientists knew stars couldn't forge elements heavier than iron through normal fusion. The universe's gold, platinum, and uranium had to come from somewhere more extreme. Kilonovas were the prime suspect, their neutron-rich debris perfect for rapid neutron capture, or the R process, where atomic nuclei gulp neutrons before decaying into heavier elements. But without direct evidence, it remained just a theory. Then came spectral analysis of this event's afterglow, unmistakable fingerprints of strontium, gold, and other R-process elements totaling maybe hundreds of Earth masses worth of precious metals. Suddenly, we knew the platinum in your ring, the iodine in your thyroid, even the uranium fueling nuclear reactors were all born in cosmic cataclysms like this. But the discoveries didn't stop there. The event also confirmed neutron star mergers as the source of short gamma-ray bursts, mysterious flashes first detected during the Cold War. And it revealed these collisions eject material at breakneck speeds, creating relativistic jets that glow across the electromagnetic spectrum. Most astonishingly, the gravitational waves arrived nearly at the same instant as the gamma rays, proving, with precision better than 1 part in 10 quadrillion, that gravity and light travel at the same speed, a cornerstone of Einstein's relativity. Yet the biggest revelation might be how common these events are. Based on this single detection, astronomers estimate neutron stars collide roughly once every 100,000 years per galaxy. Over cosmic time, that's enough to seed the universe with all its heavy elements. Every time you hold a gold coin, you're holding stardust, but not just any stardust. You're holding the ashes of 2 dead stars that tore each other apart in a fiery tango billions of years ago, flinging their precious guts across the cosmos. And thanks to that summer night in 2017, we now know exactly how that alchemy works, watching the universe mint its treasure in real time. In 2010, NASA's Fermi Gamma Ray Space Telescope was mapping the high-energy sky when it stumbled upon something no one expected: 2 colossal bubbles of scorching hot gas, each towering 25,000 light-years above and below the Milky Way center. These weren't just any cosmic clouds, they were blazing with gamma rays, the most energetic form of light in the universe, forming an hourglass-shaped structure so massive it spanned half the visible sky. Astronomers dubbed them the Fermi bubbles, and their discovery sent shockwaves through astrophysics. Here, hidden in plain sight for who knows how long, was evidence of some cataclysmic eruption from our galaxy's heart, a violent outburst powerful enough to punch through the Milky Way's disk and leave scars visible across interstellar space. The leading suspect, Sagittarius A, the supermassive black hole lurking at our galaxy's core. While today it's relatively quiet, more of a cosmic smoker than a fire-breathing dragon, the Fermi bubbles suggest it wasn't always so well behaved. One theory posits that a few million years ago, Sagittarius A went on a feeding frenzy, devouring a massive cloud of gas or even a wayward star. The resulting gravitational tantrum would have blasted twin jets of high-energy particles straight up and down from the galactic plane, inflating these enormous bubbles like cosmic balloons. But there's another, even wilder possibility. The bubbles might be relics of a starburst, a frenzied period when hundreds of massive stars formed near the galactic center and then exploded as supernova in quick succession. The combined shockwaves could have pumped energy into the galaxy's halo, creating these gamma-ray titans. What's eerie is that the timing lines up with a curious event in Earth's past. Around the same period, our planet's oceans recorded a spike in radioactive iron isotopes debris that could have been scattered by nearby supernova. Were the Fermi bubbles and this earthly anomaly part of the same galactic fireworks show? The more we study these structures, the stranger they get. Recent observations reveal they're not just filled with gamma rays, they're also emitting microwave and X-ray radiation, hinting at complex physics at play. Some of their gas might even be superheated to millions of degrees, a sign of shocks rippling through the material. And then there's the mystery of their sharp edges. Unlike most cosmic explosions, which fade gradually, the Fermi bubbles have razor-thin boundaries, as if something's corralling their energy. Could magnetic fields be shaping them? Or is there some unseen force at work? What's certain is that these bubbles aren't ancient fossils, they're dynamic, evolving structures, still carrying echoes of whatever eruption birthed them. Future telescopes, like the upcoming Cherenkov Telescope Array, might finally decode their origins by mapping the bubble's high-energy particles in unprecedented detail. Until then, they stand as a humbling reminder. Even our own galaxy, which we've mapped star by star, still holds monumental secrets just waiting to rewrite the story of our cosmic neighborhood. The Pioneer probes were supposed to be the very model of predictable motion twin robots flung toward the outer solar system in the 1970s. Their trajectories calculated down to the last decimal point by Newton's unshakable laws. So when navigators in the 1980s noticed something bizarre, both spacecraft were slowing down slightly more than physics said they should. It wasn't just a quirk. It was a full-blown cosmic whodunit. This pioneer anomaly, as it came to be known, was tiny but persistent. Each year, the probes fell behind their predicted positions by about 5,000 kilometers, a discrepancy equivalent to the width of Nebraska, barely noticeable on an interplanetary scale. But in the precise world of orbital mechanics, even a mismatch this small screamed that something was fundamentally wrong. Either our understanding of gravity had a blind spot, or some invisible force was yanking on the probes like cosmic rains. For decades, the anomaly fueled wild speculation. Could it be evidence of dark matter's gravitational tug, a flaw in Einstein's general relativity? Some theorists even floated the idea of modified Newtonian dynamics, a controversial framework suggesting gravity behaves differently at extremely low accelerations. The pioneer data seemed to fit predictions eerily well, igniting debates that spilled across physics conferences and academic journals. Here was a glitch that might rewrite the rules of the universe. Then came the plot twist. In 2012, a team of researchers painstakingly reconstructed every conceivable variable, from the probe's nuclear power sources to the faint pressure of sunlight on their antennas. The smoking gun, heat, Pioneer's plutonium-powered generators were radiating warmth unevenly, and those infrared photons bouncing off the spacecraft's rear-facing dish created just enough recoil to explain the deceleration. It wasn't new physics after all, just old-fashioned thermodynamics playing tricks on us. Yet the Pioneer anomaly's legacy endures. It taught us how easily hidden variables can masquerade as revolutionary discoveries, and how hard it is to model every whisper of force acting on a spacecraft billions of miles away. Future missions like NASA's New Horizons now account for thermal effects with obsessive precision, ensuring no more phantom forces muddy the waters. But those years of uncertainty, they were a masterclass in scientific humility, proving even our sharpest calculations must bow to the universe's endless capacity to surprise. In 1967, astronomers were stunned by the rhythmic pulses of a spinning neutron star. 4 decades later, the universe delivered another radio surprise, one even more baffling. On a quiet summer night in 2007, astrophysicist Duncan Lorimer and his student David Narkevic were sifting through old data from Australia's Parkes radio telescope when they spotted something that shouldn't exist. A 5-millisecond burst of radio waves so powerful it outshone the entire galaxy it came from. There was no trace of it before or after, just a single monstrous blip in the cosmic static. They'd discovered the first fast radio burst, an event so energetic it defied all explanation. What makes FRBs so mind-bending isn't just their intensity, it's their sheer unpredictability. Some explode once and vanish forever. Others repeat, sometimes in erratic patterns, others with clockwork precision. The most famous repeater, FRB 121102, fires off bursts every 157 days like a cosmic snooze alarm, and the distances. These flashes race to Earth from billions of light-years away, their radio waves stretched and distorted by eons of traveling through intergalactic space. So what's cranking out these extreme cosmic fireworks? Leading theories point to magnetars, supermagnetic neutron stars that occasionally snap under the strain of their own monstrous magnetic fields. In 2020, astronomers got a smoking gun when a magnetar in our own galaxy erupted with an FRB-like burst. But here's the catch: most FRBs are thousands of times more energetic than that. Could young magnetars in dense nebulas amplify their signals? Or are we seeing something even wilder, cosmic strings collapsing, primordial black holes evaporating, or dare we say it, artificial beacons from distant civilizations? The alien hypothesis, while tantalizing, faces steep odds. FRBs are scattered randomly across the sky, and their signals don't carry the telltale patterns we'd expect from technology. But the mystery deepens with the detection of FRBs emitting at frequencies too low to penetrate a planet's ionosphere, making them useless for communication. Unless, of course, their builders think very differently than we do. New telescopes are turning the FRB hunt into a gold rush. Canada's CHIME detector, a sprawling array of half-pipe antennas, now catches dozens per month. Each burst's unique fingerprint, how its waves disperse and scatter, reveals the cosmic baggage it carried. Electrons, magnetic fields, even missing matter thought to lurk between galaxies. Some FRBs even come with X-ray sidekicks, hinting at violent births alongside supernova or neutron star collisions. The most astonishing twist, FRBs might be cosmic Swiss Army knives. Their extreme brightness makes them ideal backlights to probe the universe's foggy voids. By studying how their signals warp, we've mapped previously invisible gas halos around galaxies. Some astronomers even propose using them as intergalactic GPS, timing their arrivals across multiple telescopes to measure the universe's expansion with unprecedented precision. So while we don't yet know what sparks these radio screams across the cosmos, one thing's certain: they're more than cosmic static. Each burst is a messenger from the darkest, most distant reaches of space-time, and every time we catch one, it's like the universe is tapping us on the shoulder, whispering, "You haven't seen anything yet." The idea of a single universe feels almost quaint now, like believing Earth is the only planet with life. The multiverse hypothesis, once relegated to science fiction, has clawed its way into serious scientific discourse, and it all starts with the unsettling math of quantum physics. Picture Schrödinger's famous thought experiment, a cat in a box simultaneously alive and dead until observed. But what if that paradox isn't just a quirk of measurement? The many worlds interpretation suggests every quantum decision spawns new universes, one where the cat lives, another where it dies, and countless more where every possible outcome plays out in parallel. Suddenly, reality isn't a single thread but a tangled web of alternate timelines, each equally real. Cosmic inflation, the theory that the newborn universe expanded faster than light, adds fuel to the fire. If space can inflate once, why not endlessly? Some models propose our universe is just one bubble in an infinite froth of pocket universes, each with different physical laws. Some might have stronger gravity, making stars burn out in seconds. Others could lack weak nuclear force, preventing atoms from forming at all. Most would be sterile, lifeless voids. But statistically, a few would hit the cosmic jackpot, conditions perfect for life like ours. This isn't speculation for its own sake. It's an attempt to explain why our universe seems fine-tuned for existence. Why is gravity just strong enough to hold galaxies together but weak enough not to crush atoms? The multiverse offers a chilling answer. We're just the lucky ones who ended up in a habitable neighborhood. But controversy stalks these ideas. Critics argue the multiverse is untestable, more philosophy than science. If other universes are forever beyond our reach, how can we prove they exist? Even proponents admit it's a radical leap, but they counter with pragmatic logic. Inflation's math predicts multiple universes, and dismissing them because they're inconvenient ignores the lesson of Copernicus. Every time we've assumed we're special, the center of the solar system, the only galaxy, the sole planet with life, we've been wrong. Pop culture, of course, has run wild with the concept. From Spider-Man into the Spider-Verse to everything everywhere all at once, parallel realities let storytellers explore infinite what-ifs. Yet the scientific version is far stranger. Imagine universes where time runs backward, or where entropy decreases instead of increases, worlds where broken glasses reassemble and the dead rise from graves. Some theories even suggest bubble universes could collide, leaving scars in the cosmic microwave background. Researchers are hunting for these bruises right now, sifting through the afterglow of the Big Bang like detectives examining a crime scene. The multiverse hypothesis forces us to confront an uncomfortable truth. Our universe might not just be one of many, it might be utterly average. A single page in an infinite library where every possible story is already written. Whether that's a humbling thought or an exhilarating one depends on your perspective, but one thing's certain: if true, it means reality is bigger, weirder, and more boundless than we ever dared dream. Imagine a world where rain falls from orange skies, carving rivers through dunes of plastic sand, pooling in vast seas beneath an atmosphere thicker than Earth's. This isn't a sci-fi fantasy, it's Titan, Saturn's largest moon, and what NASA Cassini spacecraft revealed there in 2005 rewrote the rulebook for where life might exist. Titan isn't just another frozen rock, it's a looking-glass Earth with one eerie twist: swap water for methane, and you've got a climate system bizarrely familiar yet utterly alien. Cassini's radar pierced Titan's hazy nitrogen atmosphere to unveil a landscape that made scientists do double takes. Liquid methane, the same gas that fuels stoves on Earth, flows in rivers, fills lakes deeper than the Great Lakes, and even evaporates into clouds that drizzle back down. At Titan's poles, massive seas like Kraken Mare stretch over 400 kilometers wide, their surfaces eerily smooth until winds whip up methane waves. This isn't just a static puddle. It's a full-fledged weather system, complete with storms, seasonal changes, and shorelines that shift as methane reservoirs evaporate and refill. But here's the kicker: Titan's chemistry mirrors Earth's probiotic era, the ancient molecular dance that may have sparked life here. Sunlight hitting Titan's atmosphere cooks methane and nitrogen into organic compounds like ethylene and propane. These molecules rain down, forming dunes of tar like hydrocarbons and possibly floating in Titan's seas. Even more tantalizing, beneath Titan's icy crust, there's likely a global subsurface ocean of liquid water mixed with ammonia, a potential second habitat where Earth-like life could cling on. The astrobiological implications are staggering. If life exists on Titan, it wouldn't drink water. It might breathe hydrogen and metabolize acetylene, thriving in conditions that would be lethal to Earth organisms. NASA's upcoming Dragonfly mission, set to launch in 2027, will send a drone-like rotorcraft to hop across Titan's surface, sampling its organic-rich soil and maybe even skimming the edges of those methane lakes. It's the first time we'll explore an oceanic world beyond Earth by flying through its skies. What Cassini showed us is that Titan isn't just a moon. It's a test tube the size of a planet, running a chemistry experiment that's been ongoing for billions of years. Whether that experiment has produced life or not, Titan's methane cycle proves one thing: the universe has a knack for taking familiar pieces and assembling them into something wondrously strange. And somewhere in those alien lakes beneath those orange clouds might lie the answer to whether life is a cosmic fluke or an inevitability. One of the most unsettling discoveries in modern cosmology isn't some distant, exotic phenomenon. It's a disagreement in our cosmic backyard. For decades, astronomers have measured how fast the universe is expanding using two reliable methods, expecting the numbers to match. They don't. This mismatch, called the Hubble tension, has become a full-blown crisis in astrophysics, one that might force us to rewrite the rules of the cosmos. The first method relies on the cosmic microwave background, that ancient afterglow from the Big Bang. By studying its faint ripples with satellites like Planck, scientists can calculate how fast the universe should be expanding today based on the early universe's conditions. Their answer: about 67 kilometers per second per megaparsec, meaning for every million parsecs of space, the universe expands 67 kilometers faster each second. But then there's the second approach, measuring the distances to nearby stars and galaxies directly. Astronomers use standard candles like Cepheid variable stars and Type Ia supernova objects with known intrinsic brightness to gauge cosmic distances. When teams like the one behind the Hubble Space Telescope crunch these numbers, they get a different expansion rate, 73 kilometers per second per megaparsec. That gap might seem small, but in the precise world of cosmology, it's a yawning chasm. At these scales, even a tiny discrepancy implies something fundamental is missing from our understanding. So what's going on? The most exciting possibility is that we're seeing hints of new physics forces or particles beyond the standard model. Maybe dark energy isn't constant but evolves over time, subtly altering the expansion rate. Or perhaps there's an unknown type of neutrino or dark matter interaction throwing off our calculations. Some theorists even speculate about a dark radiation from the early universe that left traces in the cosmic microwave background. Then there's the wild card, cosmic weirdness we haven't even imagined yet. Could spacetime have properties that change on large scales, like a cosmic viscosity or extra dimensions? Or is there a flaw in how we measure distances with hidden biases in our standard candles? The stakes couldn't be higher. If the Hubble tension holds, it means our most trusted cosmic blueprint, the lambda-CDM model that's guided cosmology for decades, is incomplete. The race is on to solve this puzzle. New telescopes like the James Webb Space Telescope and the Vera Rubin Observatory are scrutinizing Cepheid stars and supernova with unprecedented precision. Meanwhile, projects like the Simons Observatory are hunting for anomalies in the cosmic microwave background that might explain the mismatch. Either way, the Hubble tension isn't just a technical glitch, it's a crack in the foundation of modern cosmology, and through that crack, we might finally glimpse the universe's deepest secrets. Before galaxies, before planets, before even the heaviest elements existed, the first stars flickered to life in the cosmic dark, colossal behemoths that burned bright and died young, seeding the universe with the building blocks of everything we know. These hypothetical giants, called population Roman 3 stars, have never been directly observed. They exist only in theory and computer simulations, yet their fingerprints are everywhere. Picture a universe just 100 million years old, a pitch-black void filled with primordial hydrogen and helium, still glowing faintly from the heat of the Big Bang. In the densest pockets of this fog, gravity begins pulling atoms together. But without heavier elements to help cool the gas, these protostars grow monstrous, reaching masses hundreds of times that of our Sun. When they finally ignite, their nuclear furnaces burn at temperatures so extreme, they flood the cosmos with ultraviolet radiation powerful enough to rip electrons from atoms, ending the universe's dark ages in a blaze of light. The evidence for these stars is etched into the oldest quasars. Spectra of their light reveal traces of elements like carbon and oxygen materials that couldn't exist without earlier generations of stars to forge them. Even more telling is the absence of iron in these ancient signals. Population Roman 3 stars lived fast, exploding as supernova so violent, they left no stellar remnants, just pure energy and scattered stardust. Some may have even collapsed directly into black holes, vanishing without a trace. Now, the James Webb Space Telescope is poised to glimpse their afterglow. JWST infrared eyes are perfect for spotting the telltale signatures of population Roman 3 stars in distant, redshifted galaxies. Their light, stretched by cosmic expansion, might reveal unique emission lines from helium or hydrogen, untouched by heavier elements. Some astronomers even hope to catch a direct view of their death's pair instability supernova, explosions so bright they outshine entire galaxies for weeks. But the real prize, understanding how these pioneers transformed the universe. Their deaths seeded the cosmos with the first heavy elements, allowing future stars to form rocky planets and ultimately life. Without population Roman 3, there'd be no calcium for bones, no iron for blood, no carbon for DNA. We're literally made from the ashes of stars that died billions of years before our Sun was born. The hunt for these elusive giants isn't just about rewriting astronomy textbooks. It's a journey to our own origins, peeling back time to witness the moment the universe stopped being a featureless void and began its path toward complexity. And with JWST scanning the skies, we might finally meet the architects of everything. So here we are, 25 cosmic revelations that rewrote the textbooks, shattered assumptions, and left us staring at the night sky with fresh eyes. From the echo of the Big Bang to the enigma of dark energy, each discovery peeled back another layer of the universe's grand mystery, revealing not just answers but deeper, more thrilling questions. Think about it. We've mapped the cosmic web, heard black holes collide, and found oceans hidden beneath icy moons, yet every breakthrough feels like stumbling onto the first page of a story we're only beginning to read. What ties these discoveries together isn't just their mind-bending science, it's the humility they inspire. The more we learn, the clearer it becomes how much we don't know. Dark matter and dark energy make up 95% of the universe, and we still can't say what they are. Fast radio bursts scream across the cosmos, and we're left guessing who or what flipped the switch. Even our own solar system keeps surprising us with rogue planets, subsurface lakes, and maybe, just maybe, a hidden ninth world lurking in the dark. But that's the magic of astronomy. It's not about checking boxes on a list of solved puzzles. It's about stepping into the unknown, where every answer unravels new mysteries. And here's the thing, you're part of this journey too. Whether you're gazing at Jupiter through a backyard telescope or refreshing NASA feed for the latest web images, that sense of wonder is what keeps exploration alive. So stay curious. The next cosmic revelation could be just a headline away. Maybe it's proof of life on Enceladus, or a signal from another civilization, or a particle that finally cracks the dark matter code. And when it happens, you'll want a front row seat. If you've enjoyed this dive into the universe's greatest hits, hit subscribe so you don't miss what's coming next. The cosmos never stops surprising us, and neither will we. Now, over to you. Which of these discoveries blew your mind the most? Was it the violent beauty of neutron star mergers or the eerie silence of the wow? Signal, drop your favorites in the comments, and while you're at it, tell us what cosmic mystery you think we'll crack next. The universe is full of stories waiting to be told, and who knows? The next chapter might start with your idea.